First, I would like to thank the organizers for inviting to this conference. I'm going to tell you about temperature dependence of shear viscosity in SU3 gluodynamics. I think that a lot of my talk will be in parallel to the two previous ones, because I am going to describe to you some problems connected with the calculation of, for instance, conductivity, but from the perspective of shear viscosity. So this is the outline of our report, and I would like to start from the introduction. This well-known result of Rick experiment, the measurement of elliptic flow, and it turns out that if we apply hydrodynamical approximation to describe the data for elliptic flow, it turns out that it is possible to describe it, and in this case we have parameter with a shear viscosity, usually divided by entropy density, and from this measurement it's possible to get the following values of shear viscosity, allowed values. 1/4 pi is a very well-known result obtained in n equals 4 supersymmetric Young-Mills theory at strong coupling, and it turns out that coagular plasma is very close to ideal liquid with very small value of this ratio. So there are a lot of previous work devoted to the same subject. Here I show only a few of them. I'm sorry if I forgot something. And here are the results obtained in these works. The approaches was very different, and I can say that in all these approaches there is some systematic uncertainties. For instance, these two values, it seems that they are very accurate, but actually they was obtained using the fitting procedure, and we're not able to say what is the systematic of such percentage of this procedure. So we have only few values of this ratio, and it would be nice to get more values and also improve somehow our understanding, or somehow improve our accuracy of the calculation. I would like also to mention our result obtained this in 2015, measurement of S viscosity to entropy in SU2 gluodynamics, where we get very similar result to the SU3 case. And probably it means that the ratio of shear viscosity to entropy in non-abelian gauge theory are similar. So the source of these small values is the non-abelian nature of gauge theories. So let's now try. I'm going to describe the calculation procedure. It is very common. So we measure some correlation function. In particular, for shear viscosity, we should measure correlation function of energy momentum tensor, no diagonal component. Then we have this correlation function. We calculate a spectral function from these integral equations and get shear viscosity. And this is the idea in simple words. But it turns out that it is not so complicated as I described, because you know that we should reach very good accuracy of the calculation for this correlation function because of really huge ultraviolet contribution to this correlation function. And it turns out that second step is also very complicated, because we know only few dozen points of the correlation function, which should somehow extract a spectral function from this integral equation. Now the details of our calculation. So we consider SU3 gluodynamics, use two-level algorithm in order to improve accuracy of our calculation. Lattice sizes are given here, and we carry out numerical simulation for the following set of temperatures. Probably we will put few more points here. The accuracy of the calculation is from 2 to 3% at the middle point, and some other details. I'm not going to stay here. Probably you will ask questions, and then I will answer. Here's the correlation function, the measured correlation function divided by critical temperature to the fifth power. This is Euclidean time in lattice units, and these are the plots of these correlation functions. The first, in order to extract now spectral density, I'm going to first apply the simplest procedure. This is I propose some ansatz with unknown parameters, and determine the unknown parameter from this ansatz. And this is, to my mind, the simplest way how it is possible to extract shear viscosity. And in order to propose physically motivated spectral function, we should recall some properties of this spectral function. In particular, these are very general properties, and we also know that at large frequency we should expect there is asymptotic freedom. We know from a continuum, we also know that radiative correction modifies the coefficient in front of this expression. And what is very important to notice here, we saw from previous work that spectral function for the current behaves omega to the second power. Here we see that the behavior is omega to the fourth power, and for this reason the contribution of ultraviolet parts of our spectral density is extremely important. In particular, at the middle point we expect 90%, not expect, we actually can estimate it, it is approximately 90%. For this reason we need really huge accuracy of the calculation. Moreover, it turns out we carried out numerical experiment, we improved accuracy to 1%. It turns out that thus we don't improve our knowledge about infrared part of the spectral function. We improve our knowledge about ultraviolet part of the spectral function. This is a curious situation. Okay, now
is this formula multiplied with the sine of omega? Because omega to the fourth is even and rho is also.
Yes. It is a little bit more complicated. This is more simple version. Yes. I mean, this is the expression for positive omega at very large values.
Yeah, but this is even still as a function of omega.
Yes, even.
It's not even, it's large omega.
Yes, a large positive omega. I already told you. So,
okay, good.
The next important information about very small frequencies infrared part. This is we expect that at these frequencies there is a hydrodynamical approximation which is given by this formula. So, and probably the simplest way to propose ansatz is the following. So we just switch between two regimes. The first is hydrodynamics, which is switched at omega 0 with this first threshold parameter to asymptotic freedom with two parameters here. So we have actually three parameters: viscosity, threshold at which we expect switch between the two regimes, and this is coefficient which parameterize radiative correction to our expression. What is important to notice here, we could, in principle, we could use continuous expression, but it turns out that continuous expression doesn't take into account our result correctly. So it doesn't describe a result correctly because we have a discretization uncertainty in the temporal direction. In order to take into account, we use lattice expression for the spectral density. And it is possible, it is easy to calculate it, but the expression is cumbersome. I'm going to present you only numerical results. So this is the ratio of lattice spectral density at large frequencies. This continuum, we expect that, so we see that approximately from 2 to 3 divided by lattice spacing, there is a deviation, and thus we account a discretization effect in temporal direction. And it is also, it turns out that in order to describe our data, it is important to put here the coefficient because it is not 1, and it's close to 1, but it is not 1. And if we put 1 here, we will not be able to describe our data. So now let's try to fit our data. It turns out that for all temperatures under study, our description is good. Coefficient is approximately 1, but smaller, a little bit smaller than 1. And threshold parameter is from 7 to 8. And this is the result of the calculation. Uncertainties are only due to the uncertainties, statistical uncertainties in description of our data. In principle, we can propose another ansatz and try different ansatz, but I'm not going to do this because there is problem common for all these ansatzes. The point is that so we have a hydrodynamical approximation at small frequencies. One can expect that it works up to pi to temperature for frequencies up to pi times temperature. This result is based on the exact expression for the spectral density and for supersymmetric theories, and there it works, hydrodynamics works up to these frequencies. We also expect that asymptotic freedom probably works up from 3 GeV, and so we can say that in the region from 1 to 3 GeV, we have poor knowledge of our spectral function, and this probably is the main source of the uncertainty in all fitting procedures. So in order to somehow improve our result, I propose another approach which is quasi-model dependent. This is Backus-Gilbert method, and briefly, this is we measure correlation function. We want to determine spectral function. Then instead of this spectral function, we propose estimator for the spectral function. This is actually spectral function average over some interval. Omega bars here is the position of the peak of this resolution function, which is designated as delta. So this function is expanded in terms of this kernel at different points. And if we now plug in this expression to this one, we will get that estimator for the spectral function is just a linear combination of our values of the correlation function. And how to determine this coefficient? We just need to minimize the weights of the resolution function, because if our resolution function is delta function, we get exactly the result what we actually needed. And so we carry out minimization of the weights, and thus we determine the values of the coefficient. What is important to note is here that it is not possible to apply this procedure directly because of the uncertainties of the calculation, and we use regularization by covariance matrix. So we have some matrix, and we introduce regularization with some parameter lambda. Now we apply this approach. This resolution, we actually need only ratio viscosity to entropy at zero frequency, and this is a resolution function at zero frequency. This is misprint. This is omega divided by temperature actually. So we see that the width of this resolution function is 4, and we expect that hydrodynamics approximation works up to pi. So we have a good, average or good interval. But what is very important, it seems that there is no contribution from large frequencies, but actually this is not the case, because we should multiply by omega to the fourth, and this, for this reason we have contribution also coming from large frequencies. Our estimation gives a result of order of 50%. And to solve this problem, we propose a model for the ultraviolet tail of our spectral function. Here we have two independent parameters. This is A, this is omega 0. The omega 0 can be very accurately determined, for instance, from the from the correlation function at very small Euclidean times. But it turns out omega 0 is very difficult to determine with good accuracy. So we plot this ratio, shear viscosity divided by entropy, as a function of this omega 0. So we have such plot. By the way, if, for instance, we could expect transfer peak at zero frequency, in this case we should expect, on this plot, we should expect some plateau, but we don't see it. For this reason, I think that there is no transfer peak for shear viscosity. So now, how to determine omega 0? We determine omega 0 from the fitting procedure I have described you above, and this is 733 plus minus 0.74. Thus, we determine with uncertainty this ratio, and our result, for instance, for the temperature, critical temperature, is given by this value. So this is the result of the calculation. Green points, Backus-Gilbert method. Fitting procedure. Red points, Backus-Gilbert method. Blue line is n equals 4 supersymmetric and mu theory, and experimental bound is given here. So I come to the conclusion. So we calculate shear viscosity for the set of temperatures, applied fitting procedure and Backus-Gilbert method procedure in order to describe, in order to find shear viscosity, and we found that this shear viscosity to entropy ratio is close to n equals 4 supersymmetric Young-Mills theory in good agreement with the experiment. And Probably you remember some papers where the authors also observe drop of this ratio to the critical and then very slow rise. So we also observe it in our simulation. Thank you very much.
You were too quick. So we have lots of time for discussions. Szabolcs?
So perhaps I can comment on this from the lattice point of view. So it was a perfectly reasonable assumption to have this flat spectrum. Like the transport coefficient takes a constant value and it rises with the perturbative expectations. And this is the best one can do. Although, if you go to very high temperatures, you expect some quasi-particle behavior, as we learned from the Hartmann loop, there will be a transport peak.
Mm-hmm.
So you need to know where it appears, but from the lattice calculation, as we learned last week at the lattice conference, it is not in the data. So you would need about 100 times more statistics in order to see whether there is a transport peak or if there is no transport peak. So to get a temperature dependence, since the bulk of this temperature dependence would come in the presence of, from the presence of this peak, you will not find from the data. And this is where we are in lattice field theory. And it cannot be really improved because no one will have ever 100 times or 1,000 times more statistics that we have.
The point is that we actually carry out, I already told, that we carried out a numerical experiment. We improved the statistic. But this doesn't lead to the improvement of our knowledge in the infrared part of the spectrum. It improves the knowledge in the ultraviolet. So I don't know how much we should improve. Probably it is better to enhance the number of points in temporal direction.
That won't help. That has been shown that if you simply divide Euclidean correlator by with a ITEP spectrum, a transport peak, by a Euclidean propagator with a transport peak, then the ratio is 1 plus minus 2 promille. So it is in the data and it is in the fourth digit. And it has absolutely no dependence on the lattice details. It is just Euclidean physics. So you need some input that there is no transport peak, which is reasonable to see. That's the best one can do.
Olaf?
Yeah, maybe in addition to this comment, as I showed in my talk, is that if you take a flat spectral function, this gives more the lower limit of the transport coefficient.
Yes.
So if you would do the fit with a real transport peak, you would get higher values. So I guess the uncertainty is quite large, and I guess it's more like the lower limit that you get.
Yes, yes, I agree. The point is that if we, for instance, fitting with but we tried actually to apply spectrals, for instance, to propose some function with a peak at zero frequency, but it turns out the minimal chi-squared values when this peak is flattened, so it is so it means that there is no peak at all, at least from the our data. And for instance, we can consider this spectral function as a upper bound for the shear viscosity, because if you, for instance, so we have constant spectral function. If we divide rho divided by omega, we have some constant to very large values of omega, but actually we can expect that it rises, because we have ultraviolet, which scale is omega to the 4. It means that this estimation probably is the upper bound for the shear viscosity.
Yeah, I would more argue that it's a little lower bound. Also to your asymptotic freedom, you said that you assume asymptotic freedom from 3 GeV on. That I don't believe. In principle, you should put some perturbative calculation in there.
To my mind, perturbative. 3GV is good, for instance, from our experience of QCD sum rules. 3GV is good scale for starting of asymptotic freedom. Moreover, what is very important that we have fitting procedure, and we expect, so from fit, we also expect from 7 to 8, something like that. It depends, sure, probably it is better to say that this omega 0 divided by T is constant for all temperatures under consideration. It means that effectively it rises with temperature.
René, here. Agostino, on the other side. René.
As an experimentalist, you always get a little nervous when a quench calculation agrees with your data, because then you kind of get to draw the conclusion that the quarks don't matter. Do you expect a change if you would have quarks in your calculation? Or?
So, as far as I understand, nobody knows, because inclusion of so in the calculation we applied two-level algorithm in order to get good accuracy. But it turns out it is not possible to apply two-level algorithm if you input quarks. For this reason, we are not able to reach this accuracy of the calculation. For larger accuracy, everything will be described by ultraviolet or asymptotic freedom.
Are there more questions? Where's one?
Just want to understand the uncertainty of your calculation more. Have you tried to explore uncertainty from Bacchus, Gilbert, and Lasser?
I have already told you that
use one number, right?
the point is that we don't know. We thought that Bacchus-Gilbert method will be sufficient to determine the ratio with good accuracy, but actually this is not the case. This is not the case because we don't know this threshold parameter very well. This is the point. We don't know how much we should subtract of ultraviolet contribution.
There's a comment on that.
Okay.
This expression obtained from the fitting, so we somehow extract from the fitting procedure with the function I have already showed you, and this value was obtained from this fitting procedure.
Yes, so there's a comment on that, because you subtract this the ultraviolet thing, but for the Bacchus-Gilbert you ideally want the thing to be flat in rho over omega squared. So you could also rescale the kernel, get this as flat as possible, and your transport peak would then be a bump in the low frequency region, and your average spectral function, which is 5 temperature units wide, would hopefully show a small deviation from this constant. So I don't know why you did this omega 0 subtraction. I think you could have also rescaled the kernel and seen, and you would get rid of this problem then, like that. Just as a comment.
Okay, that's very interesting. So
Yes,
let's
very interesting. We will try to do something like that.
let's thank Victor again. Now, next speaker is Yusuke Taniguchi. Yes. Sorry. And he'll talk about the energy momentum tensor from gradient flow.
Thank you very much.
When we are ready.
Yes. Thank you very much.